Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Okay, thank you, Dr. Gu, for the kind invitation and nice introduction. It's a real honor to be part of the talk at EEH. I'm honored. Well, good evening, everyone. I am Wenqing Su. I'm currently an associate professor at Villanova University. We're situated in the beautiful suburb of Philadelphia. And I really hope that after today's talk, some of you might have some interest in coming here to study or to visit. So without further ado, today I'm going to talk about my group's endeavor in developing a polymer network to really understand the reactivity of carbonaceous material towards contaminant transformation. This area has broad implications on water and sediment management, which I'll talk about it later. So just to spend a little time to bring everyone on the same page, what is PCM, which I refer to as pyrogenic carbonaceous matter? I'm sure a lot of the audience are familiar with this term, especially if you're working with water and sediment management. By definition, they are the solid residual from incomplete combustion of fossil fuel and biomass. And two well-known examples of PCM are activated carbon and biochar. The conventional wisdom is PCM are passive adsorbents, and due to their large surface area, high pore volume, and their diverse functional group. They have been widely used in various engineering applications. For instance, in water treatment, PCM in the form of activated carbon have been traditionally used in the filtration step to remove recalcitrant organic contaminants such as the disinfection byproducts and some of the disinfection byproducts precursors. PCM is also widely used in groundwater remediation. This graph here shows the packed bed of activated carbon, which is widely used in the pump and treat technology to sequester contaminants such as chlorinated solvents and also PFAS, which is gaining a lot of attention globally these days. In addition, PCM in the form of activated carbon and biochar are also used as sediment amendment to stabilize PAH and PCBs in soil. Another sector which has gaining a lot of attention is the application of biochar in the agriculture fields, which tend to retain water and nutrients while provide this carbon sequestration benefits. So one thing to point out is all of those applications are based on one key assumption, which is PCM is a passive adsorbent. In other words, once the contaminant gets stripped from the aqueous phase, it stays on PCM surface without going through any transformation. That means once the absorption sites are saturated, what do? So that raised the important concern of PCM application in engineering fields is the disposal and regeneration of PCM. And without a doubt, that will add a lot of cost, which is why it incentivized the looking for alternative technology. Interestingly, in the past 10 years, there's a small but growing body of literature suggests that PCM itself is actually not really that inert. It is intrinsically reactive. There are a lot of studies that demonstrated PCM can mediate redox reactions. For instance, as I illustrated here, PCM can act as electron shuttle to transfer electrons from reducing agent, which often present in the natural environment, such as hydrogen sulfide minerals, and shuttle the electron to contaminants. PCM can also act as an oxidant, which can convert bisulfide to more reactive sulfur species, such as polysulfide, which result in contaminant decay. Altogether, people have observed the enhanced decay of azo dyes, nitrate, chlorinated solvent, herbicide, and safeners. In addition to PCM-facilitated redox reaction, PCM can also facilitate surface hydrolysis. There are not a ton of literature on this aspect, but the existing ones have demonstrated PCM can convert tetrachloroethane to TCE and could also enhance the base hydrolysis of methylbromide and TNT. However, what key properties of PCM is responsible for these observed reactivity is still unclear. How so? If you look at this structure of PCM here, you probably would agree with me, it is very rich in physical chemical properties, right? So for instance, PCM is well known to have redox active moieties such as quinone and hydroquinone pairs. They're well known to be able to mediate redox reactions by shuttling electrons. We also know that the polyaromatic ring clusters, as you can see here, which contributed to the conductivity of PCM, can also facilitate electron transfer at a faster rate through the solid matrix. In addition, PCM has a lot of different functional groups, which contains either oxygen or nitrogen. Last but not least, PCM has a range of pore characteristics, which contains as small as micropores, which is below 2 nanometer, all the way to metal pore from 2 to 50, and macropores that is above 50 nanometers. And all those different pore size might also have an effect in contaminant transformation. However, when you look at PCM, all those properties are intrinsically linked. So it is very difficult to understand which properties are responsible for the observed contaminant transformation. As a result, we need an approach to be able to delineate the contribution of each property. And that leads to our group's work in the past 10 years, maybe not 10, probably 5, where we developed this tunable PCM-like polymer network, which I'll refer to as PLP. Similar to PCM, PLPs have large surface area and high microporosity, and this image shows a synthesis of PLP. It is also highly conjugated, just like PCM, and it is amorphous. On top of that, it has superior affinity towards apolar contaminants. Unlike PCM, though, we can tune the functional group identity, pore characteristic, and conductivity of PLP individually. For instance, this is a synthesis route for the PLP we did in our lab. And as you can see, we can tune the functional groups through the selection of the linker here. And the specific functional group can be incorporated through the R group, which can either be OH, NH2, but it will be individualized. We can also tune the pore characteristics of PLP. For instance, this top route for synthesis, where we use the 3-pronged monomer struts, will produce cross-linked polymer, which has more of a microporosity. If we choose the monomer strut to be 2-pronged monomer strut, we will generate linear polymer, which will have less microporosity, but more of a metal porosity, which I'll talk about in the part 2 of my talk, how we utilize that to understand the impact of pore geometry on contaminant transformation. Last but not least, we can also tune the polyaromatic ring cluster size through a process called pyrolysis. So by increasing the pyrolysis temperature, we can manipulate the average ring cluster size and therefore change its conductivity. All right, so now, based on all those backgrounds, I'm going to talk about 2 papers published by my group in the past few years, where in part 1 of my talk, I'm going to focus on how we use the PLP to understand, to delineate the redox properties of PCM, specifically the quinone-hydroquinone pair and the polyaromatic ring system. This work is published on EST, and the DOI is provided here. In part 2, I'm going to talk about how we use the PLP to understand and identify the key PCM properties in enhancing surface hydrolysis. This work is just published on Applied Catalysis B, and the DOI is provided here. All right, so let's focus on the first one, the redox properties of PCM. We are particularly interested in 2 redox properties of PCM, as I mentioned. One is the electron exchange capacity. That is mostly presumed, that is mostly coming from the quinone and hydroquinone pair based on existing work. So in this case, we synthesize the PLP0, which has no functionality. And then we synthesize the PLP-OH, where we incorporated the quinone and hydroquinone pair through the R group during the synthesis. And we call this PLP-OH. As expected, as you can see from the contact angle, the polymer becomes a lot more hydrophilic as compared to the PLP0. It is very hydrophobic. And we presume PLP0 and PLP-OH would have different electron exchange capacity. We also are interested in the polyaromatic ring cluster and how the conductivity would affect contaminant transformation. So here, we took the PLP0 and we pyrolyzed it under 4 different temperatures, from 600 all the way to 900. We expect to see a continuous increase in the average ring cluster size and also in conductivity. So now we have 6 PLPs. We will monitor the reactivity of PLP by quantifying the decay rates of a model contaminant, which is trichloronitromethane. This is a fungicide, and it is also a disinfection byproduct. The beauty of this contaminant is it decays in the presence of PCM and PLP alone at neutral pH. So we basically monitor the disappearance of TCNM in the bench reactor and use that as a surrogate to understand the reactivity of PLP. I want to point out up front that we monitored the total mass of TCNM and other contaminants in our work by basically summing up the amount in the aqueous phase and the amount extracted from the solid phase. So the disappearance of the contaminant in this way, we can be sure it is due to transformation rather than adsorption. Okay, so with that, let's take a look at the 6 PLP. We first characterized them using solid state NMR to make sure they are what we think they are. The PLP0 and PLP-OH are shown here. There are a couple of interesting observations or important observations I want to point out. So first of all 3 peaks from 90.8, 123.7, 131.8, they are indicative of the successful formation of the conjugated polymer network. And if you're looking at the PLP-OH, it has 2 additional peaks showed up. The 167.8 is suggests the presence of phenolic groups, and the 196.2 suggests the presence of carbonyl group, which shows the successful synthesis of the incorporation of the quinone hydroquinone pair. On the right-hand side, that's the 4 PLP pyrolyzed from different temperatures. Interestingly, you can see that the peak from 90.8 disappeared. Instead, all the small peaks merged into a large, broad peak from 100 to 165, which is in line with prior work. And based on this result, we can actually calculate the aromatic index using the peak ratio as shown in this equation here. And the results for all 4 PLP are summarized in the table below. As you can see, as the pyrolysis temperature increases, we do see an increase in the aromatic index number, which suggests that the average ring cluster size increased. We then used a 2-probe packed carbon bed to measure the conductivity, which is in line with what we have got from the solid state NMR. So overall, this result suggests that the synthesis is successful, and we now have PLPs that is not conductive, but they feature quinone and hydroquinone pair, and we also have PLP that is conductive. So then we want to understand their reactivity. So this is an example where we monitored the transformation rate of TCNM and also characterized its products. So the y-axis, as I mentioned earlier, is the total amount of mass of compound. So in the presence of PLP 800, we can see a rapid degradation of TCNM, and we observed a complete transformation of TCNM in the first 20 minutes. We observed several products. One is the DCNM, which is a dichloronitromethane. And we also observed the monochloronitromethane in blue here. At the same time, we observed the release of chloride into the system. Overall, we obtained pretty good mass balance on chlorine atom. Based on the product information, we propose what happened here is the TCNM underwent reductive dechlorination pathway, where we can see the stepwise dechlorination that generated DCNM and CNM. We then conducted pH effects. So we increased the pH from pH 7 all the way to pH 10. As you can see from the figure on the right, the reaction rate decreased as pH increased, which further supports the reductive dechlorination pathway as I illustrated here. All right, so We then want to understand what properties of PCM matters. So we conducted correlation analysis between the reaction rate constant and different properties. One is the electron donating capacity of the PLP, one is the conductivity. As you can see from the left-hand side, there's really no apparent correlation between reaction rate and EDC. However, we observe pretty good correlation between reaction rate and conductivity, and that suggests the conductivity in this case is a lot more important than EDC. What is very interesting is if you're looking at PLPOH, as I am using the mouse to hover over, you can see it has pretty high EDC value as we expected. The PLP0 has basically no EDC value because it has no functionality. But then if you're looking at PLP here, it also has no reactivity, which means although the PLPOH has the pool of electrons as reflected in its electron donating capacity, it resulted in no reactivity because very likely the electron transfer kinetics at the interface is the limiting factor, and that's why conductivity matters. All right, so with that, I'll move on to part 2, where we looked into the key PCM properties in surface hydrolysis. So in this work, we're particularly interested in 2 things. One is the functional group identity, and one is the pore characteristics, and how would they individually impact the surface hydrolysis. So regarding the functional groups identity, we are particularly interested in 4 different functional groups: OH group, NH2, tertiary amine, quaternary ammonium. So we synthesized the PLPOH group in the same way as I just described in part 1. And then using the OH group as an anchor site, we're able to graft the quaternary ammonium group, which resulted in this PLP quaternary ammonium group showing in red. We also synthesized the NH2 group by through the incorporation of the R group, as I previously discussed. And then we methylated the NH2 group into the tertiary ammonium, into the tertiary amine group, which is shown here. So that's how we obtained the 4 PLP with different functional groups. We also wanted to understand the impact of the microporosity in contaminant transformation. So we utilized different monomer strut and synthesis time. At the end of the day, we were able to obtain PLP NH2 and PLP micro, the left 2. They're a mixture of micropore and metal pore. And the PLP metal is a polymer that has no microporosity, which is synthesized from the same pot as PLP micro, which will be used to understand the impact of the pore geometry. Once we obtained the 6 different PLPs, we quantified the reactivity of these PLPs by monitoring the disappearance and transformation products of TNT, which has been reported in previous study to undergo PCM facilitated surface hydrolysis. We also looked into pH effect, and we carried out some computational study to understand the reaction mechanism. All right, so similarly, we want to first make sure we did obtain the PLPs we desired. As you can see, the 4 PLPs with different functionalities, they also again showed the 3 peaks showing in purple here. They are, as I mentioned, indicative of the successful synthesis of conjugated polymer system. For PLP quaternary ammonium group, we can see a strong signal at 53.5 in red, and that is a carbon bonded with the quaternary ammonium group. And PLPOH showed the same peak at 167.8, that is the phenolic group. And PLP tertiary ammonium group, tertiary amine group has a signal at 44.1, and PLP NH2 group has a peak at 144.2. I also compiled the pore distribution analysis here. As you recall, the top two, PLP NH2, PLP micro, they have a mixture of microporosity and metal porosity, as you can see from here. This is the microporosity here, and the rest are the metal porosity. What is interesting is if you're looking at PLP metal, which is in green, it has no microporosity. So this will be used as a comparison point to understand the role of microporosity here, right? So then we monitor the decay rates of TNT in the presence of PLPs with different functional groups. So the y-axis is, again, the total mass of TNT. And the way I plot it, the slope is the rate constant. So as you can see, so at pH 7, there's actually no decay of TNT without adding PLP. But once we add PLP in the system, we can see different extents of degradation. And the fastest is the PLP with quaternary ammonium group, followed by PLP NH2, followed by PLP OH. And the tertiary amine showed very little reactivity during the time frame of the investigation. We propose the observed trend can be explained by the formation between the TNT and the surface functional group, which resulted in a Switter ion, which is a sigma complex. And OH minus is known to be able to catalyze the reaction to the products. So that's why we observed the NH2 to be faster than OH, because when they're both in the protonated, in the neutral form, this is actually a stronger base than the OH. Another interesting observation is if we're comparing the black line versus the red line, recall what I mentioned during the synthesis process is the quaternary ammonium PLP, which is PLP in red, is simply used the OH group as anchor site to add the quaternary ammonium group. So they're actually synthesized from the same material, with the only difference being the red polymer with has additional quaternary ammonium group. So simply by doing that, we can see a pretty big enhancement factor. At pH 7, we saw 4 times faster degradation rate by simply adding quaternary ammonium group. And the effect becomes more significant at pH 9. It's actually 10 times faster than with quaternary ammonium group than compared to the PLP with OH group alone. So we hypothesize that the quaternary ammonium group can accumulate OH near the surface and therefore create a local high pH that facilitate the base hydrolysis. We also evaluated the effects of different pore characteristics of PLP. So as you recall, the left two, PLP NH2, PLP micro, has a mixture of micropore and metal pore. And the PLP in green only has metal pore. So as you can see on the left, both the PLP with a mixture of micropore and metal pore resulted in the fastest decay of TNT, versus the PLP contains only metal pore resulted in slower TNT decay. The formation of nitrite is shown here, which mirrored the same trend, which suggests that the micropore of PLP is very important in facilitating TNT decay. And we hypothesize it could be due to the nano confinement, where it changes the orientation of the molecule to make it more susceptible to hydrolysis. So we then carried out some molecular dynamics modeling to understand what exactly is happening. So we used the 4 layers of graphene sheet, which are shown in the black dots here, and we kept the sheets at 5 nanometers apart to represent a simple geometry of PCM. We filled the gap with electrolytes, and water is shown in red, and hydroxide is shown in blue. TNT is shown in green, So for simplicity, we didn't show the water molecules for B, C, and D. But from panel B, C to D, we start to decorating the surface with quaternary ammonium group, which is shown in purple here. And we increased the density from B, C, all the way to D. There are a couple of really, we also, to maintain the system as neutralized, we also added chloride, which is shown in orange here. There are a couple of really interesting observations here. As you can see on the pristine graphene sheets, TNT tend to lie flat. But as we decorate the surface with more and more quaternary ammonium group, TNT got pushed off the wall, and in the end, it aggregated in the middle of the pore. At the same time, the density of OH minus hydroxide started to build up near the wall. If you're looking at panel C, what is interesting is that TNT was pushed off the wall and ended up in the same spatial region where OH minus is 4 times higher than the middle of the pore's OH minus concentration. So we propose that's why we have observed these enhanced surface hydrolysis, and that is due to the impact of QA group resulted in the near the wall higher pH effects. So with all those findings, how do we translate that into practice? So far, I believe most of you are convinced that the QA group, the quaternary ammonium group, is important. So we decided to craft that onto activated carbon. So we took granular activated carbon and we soaked it with polydetmac, which is widely used in water treatment industry as a coagulant, and it is largely regarded as non-toxic. Because of the strong interaction between polydetmac and granular activated carbon, it will anchor positive charges on the surface. So this is called modified GAC, and the pristine GAC's result is shown on the right. As you can see, by simply coating the surface with quaternary ammonium group, we were able to reduce the half-life of TNT from 1 day all the way to 0.2 day. And at the same time, the amount of nitrite formed in the modified GAC is twice as much as the pristine GAC. So all of that is interesting and exciting. And then we decided to perform a challenging test, which is shown in the panel C. What we did is we saturated the surface site of GAC with TNT. As most people in the environmental field, that is very unrealistic. That's why we want to really stress the system to see how would the system perform under, a lot of pressure. So we saturated the surface site with TNT, and we added TNT for 10 successive additions. As you can see, the blue bar is the amount of TNT added every time. And the red bar is the amount of TNT remaining, and the green bar is the amount of nitrite formed. So although this is a very extreme condition, we still observed over 90% TNT degradation after 10 consecutive cycles, which is promising. And at the end of the day, we did see some decrease in GAC performance, which is likely due to the blockage of the reactive sites. If you remember, I talked about this formation of sigma complex that would essentially block the reaction site. All right, so I guess I'm just going to stop here and reflect a little bit. So for the past few years, we've been really trying to understand this key question. What is the key properties of PCM? That is important. So we used this PLP platform to individually assess the contribution of functionality, porosity, and conductivity in the observed contaminant transformation. And the goal is really not to deploy PLP, but rather to translate the knowledge for PCM design, right? So at the end of the day, what we envision is if we understand what properties matter, we can populate that property to produce more reactive PCM, which can be deployed for groundwater remediation, soil amendments, and also in drinking water and agriculture sector. So if I take the example of the second part here, what we found is the QA groups can accelerate surface hydrolysis, and we can potentially craft QA in more abundance on the GAC to increase the surface hydrolysis. And we also found that there's also this formation of sigma complex between NH2, OH, and TNT. So if you're interested in remediating nitroaromatics, you definitely want to minimize the presence of those functional groups because they probably contributed to the decrease in the GAC performance in the end. So with that being said, the more we understand at a molecular level what is happening, we can better design the system to really facilitate the work in sustainable water and sediment management. All right, so I want to thank all my student, Zhao Pan here, who did a lot of the work, and also those collaborators here who are instrumental in making the research going. I also want to thank my funding agent, my NSF Career Award. I'm also funded by NIH and CERDP. All right, so I'm happy to take any questions.